Have you ever really stopped to think about how your computer works? I mean, how it goes from a chunk of metal and plastic to something that can play a movie or connect you with someone across the world. It feels like some kind of magic, but it's not. It's actually pure, predictable logic. So today, let's pull back the curtain and see how computers really think.
You know, deep down, at the very heart of it all, every single digital device is made up of billions, and I mean billions, of tiny little switches called transistors. Each one can either be on, which we call a 1, or off, which we call a 0. That's it. This simple on or off language is the foundation for absolutely everything. But the key is, computers don't just store these ones and zeros, they actively process them, turning a bunch of inputs into a meaningful output.
So that's the big question, right? How do we go from a simple on-off switch to something as incredibly complex as a web browser or a video game? Well, the answer is that we teach those switches the rules of logic.
And that's where these things called logic gates come in. You can think of them as the absolute basic building blocks of any computer circuit. A logic gate is basically a tiny decision maker. It looks at one or more inputs, those ones and zeros we talked about, and then spits out a single output based on a very specific rule. This is how we get a simple switch to start thinking.
Okay, so let's get into the fundamentals, the basic grammar of digital logic. We're going to look at the most common gates that pretty much all of computation is built on.
What's so cool here is just how simple these rules are. Take an AND gate. Its output is 1 only if both of its inputs are 1. That's it. Then you have the OR gate, which is a bit more relaxed. The output is 1 if either of its inputs is a 1. And finally, the NOT gate, people often call it an inverter. It's the simplest one. It just flips the input. A 1 goes in, a 0 comes out, a 0 goes in, a 1 comes out. And believe it or not, with just these 3 simple rules, you can build a computer. But the real power comes when we start connecting them together.
And this, right here, is where the real magic happens. When the output of one gate becomes the input for another one, we've created what's called a combinational logic circuit. The result from one decision flows right into the next. It's this simple act of chaining them together that lets us build up from basic rules to incredibly complex behaviors.
Now, a circuit like this can look a little intimidating at first. You've got multiple inputs, gates feeding into other gates. Trying to figure out that final output, Q, just by looking at it can feel like a real puzzle. But don't worry, there is a totally systematic way to solve it every time.
So, before we can solve the circuit, we need a reliable system. We need a way to map out every single possible combination of inputs that could ever exist. And for that, we use a really powerful tool called the truth table.
Okay, so how many combinations do we actually need to check? Well, there's a really simple formula for that. It's 2 to the power of n, where n is just the number of inputs. In our case, we've got 3 inputs, A, B, and C. So we have 2 to the power of 3, which comes out to 8. So we know our truth table is going to need 8 rows.
Now, trying to write out all 8 combinations without missing one or accidentally repeating one, it can be tricky. But there's a fantastic little trick for this, which the Engineers Academy calls the half and half rule. It's a completely foolproof way to get it right every single time.
Here's how it works. It's super easy. In our first column, A, we've got 8 rows, right? So we just fill the top half with 4 zeros and the bottom half with 4 ones. Then for the next column, B, we just have that pattern. So 2 zeros, 2 ones, 2 zeros, 2 ones. And for the last column, C, you guessed it, we have it again, and just alternate 0, 1, 0, 1, all the way down.
And check it out. This is the result. Without having to think or double-check, we are guaranteed to have every single possible combination, from all zeros to all ones, laid out perfectly. This systematic approach is the bedrock for solving our circuit.
Let's see how this works. Now that we have all our possible inputs mapped out, we can finally start to tackle the logic circuit itself. And the key here is not to let it overwhelm you.
You know, the biggest mistake people make is trying to solve the whole thing at once in their head. The real solution is to divide and conquer. We're just going to solve one little piece of the puzzle at a time, and that makes the whole process way easier and way less likely to have errors.
So the secret weapon here is that we introduce an intermediate step. We literally create a new column in our truth table, let's just call it P. And that column represents the output of the first gate in the circuit. This breaks one big scary problem into 2 small simple ones.
All right, enough with the theory. Let's actually see this method in action.
We're going to walk through a complete example from start to finish, using both the half and half rule and our new intermediate node method.
So here's our circuit. We've got 3 inputs, A, B, and C. The inputs B and C go into an XOR gate. Now, XOR just stands for exclusive OR, and its rule is simple. It only outputs a 1 if its inputs are different. Then, the output of that gate, which we're going to call P, goes into a NAND gate along with input A. And a NAND gate is just the opposite of an AND gate. It outputs a 0 only when both of its inputs are 1. Our final mission is to figure out the output, Q.
Okay, first things first, let's solve for our intermediate node P. For now, we're going to completely ignore column A and just look at columns B and C. The XOR rule says we're looking for rows where B and C are different. So the first row is 0 and 0. They're the same, so P is 0. The next row, 0 and 1, they're different, so P is 1. We just follow that simple logic all the way down the P column.
And now for the final step. To find Q, we can totally ignore the B and C columns. We only care about the inputs going into that NAND gate, which are column A and our new intermediate column P. And remember the rule for a NAND gate. We're looking for any row where A and P are both 1 because that's the only time it will give us a 0. Every other combination gives us a 1. So we just scan down, find those rows, and mark the Q outputs as 0. All the rest are 1.
And there you have it. We've done it. We've calculated the final output Q for every single possible combination of inputs, just by breaking a complicated problem down into simple, manageable little steps. It's not magic, it's just a process.
So let's just zoom out for a second. What we just did for that one tiny 2-gate circuit is, in principle, exactly how the most powerful computers in the world do their work.
Every single amazing thing your computer does is built on this foundation. It's just this simple, logical, step-by-step evaluation of inputs based on fixed rules, but it's happening billions of times per second across billions of transistors. All that incredible complexity comes from a massive scale of pure simplicity.
And that kind of leaves us with a pretty fascinating thought. This entire digital universe that we've all built, from global communication to artificial intelligence, it all boils down to just a few simple rules, repeated over and over and over again. It makes you wonder, what other complex systems in our world are secretly being governed by a few surprisingly simple logical rules?